Hey everybody, this is Rob Munoz. Today you're listening to a presentation on fullerenes. This was made for the course MENG477 here at Gonzaga University. It's taught by Dr. Pat Farrow, also known as Advanced Materials. It was written by myself, Derek Klopp, Courtney Quinn, and Peter Auerbach. So this dude Buckminster Fuller is where the fullerene gets its name from. He was an architect around the 50s, and he came up with this idea of the geodesic dome. The geodesic dome is essentially a sphere that is derived from this shape called an icosahedron, which is a bunch of little triangles put together in 3 dimensions. What he did is he chopped off the top of each of these pyramids, and it became a soccer ball, essentially. So the word fullerene really refers to any sort of a carbon molecule that is in the shape of an ellipsoid sphere or a tube. So before we get into the fullerene itself, we should actually talk a little bit about the history behind it. These 3 guys, Robert Curl, Harold Kroto, and Richard Smalley, in 1985 explored the formation of long carbon nitrogen molecules discovered while observing carbon-rich stars. They came across the C60 molecule, otherwise known as the buckyball. In 1996, these scientists won the Nobel Prize in Chemistry, and in 1991, carbon nanotubes were first discovered. These are the major events in fullerene history. So, before we really get into the fullerene itself, it's also wise to talk about the carbon atom. The carbon atom, like any atom, has 3 kinds of particles: neutrons, protons, electrons. Protons and neutrons exist at the center of the atom, also known as the nucleus, and electrons orbit around that nucleus. The carbon atom has exactly 6 electrons, 6 neutrons, and 6 protons. We'll see why that's important shortly. The electrons orbit at different distances from the center. The ones furthest away from the center are called valence electrons. They help the atom to bond with other atoms. The carbon atom can have 4 different kinds of bond configurations. It can have 2 double bonds, 4 single bonds, 2 single bonds and 1 double bond, or 1 triple bond and 1 single bond. Alright, check this out. So, Buckminster's building is sort of like a special kind of carbon molecule. A kind of molecule known as an allotrope. Allotrope just means a molecule is composed of all one element. In this allotrope that we're about to discuss, there are 60 carbon atoms, all of which have 2 single bonds and 1 double bond. The allotrope is named after Buckminster Fuller, and it is known as the buckyball, or C60. In this picture, you can see the 60 carbon bonds in 2 different forms. So, C60 molecules, aka buckyballs, are an incredibly interesting group of materials. Buckyballs are extremely resilient. There's no harm done to them after they slam into a stainless steel plate at 15,000 miles an hour. Also, they're extremely hard when they're compressed and can become twice as hard as diamond. Diamond is actually the hardest material that naturally occurs, unless you consider buckyballs to be natural, which can be the case. They can occur in fires or through lightning. It's also important to note that C60 is the parent molecule of C70 and other higher variations. Kroto had been studying long carbon chains found in space. To test the hypothesis that these came from carbon-rich red giant stars, he wanted to use Smalley's laser-generated supersonic cluster beam apparatus, also known as AP2, to vaporize carbon and to study the clusters of carbon produced. The first results of their experiments were long carbon snakes that Kroto had sought. However, their grad student assistants noticed an unusual peak in the mass spectra of the clusters formed by the AP2, which showed an abundance of molecules composed of 60 carbon atoms, C60. Such an abundance suggested that the stability of this macromolecule. Knowing the chemical makeup is not the same as knowing the structure, so the scientists had some thinking to do. Trying to find a stable structure, Smalley resorted to the method of scissors and tape and inserted some pentagons into the structure, prompted by Croto's recollection earlier that day of having once made a paper star dome for his children that included pentagons as well as hexagons. Smalley's result was a polygon with 60 vertices and 32 faces, 12 of which are pentagons and 20 are hexagons. So Richard Smalley absolutely deserves credit for coming up with the first method to vaporize carbon and produce C60 molecules. However, he was only able to produce very small quantities, so much so that he was unable to study the molecule's properties. The Max Planck Institute and the University of Arizona collaborated and developed a new method in which 2 graphite electrodes were consumed in a helium or neon-filled chamber. The consumption of these electrodes results in a production of a black soot. This black soot contains buckyballs but is not purely buckyballs. So, a benzene solvent has to be used to separate the two substances. In more recent years, vaporization has been completely bypassed altogether by MIT and NanoC through the use of a hydrocarbon-oxygen mixture. Carbon nanotubes have some really interesting structural properties. Among other things, they are known to be 300 times to have 300 times the strength-to-weight ratio of steel. Steel is 6 times as dense as a carbon nanotube, and yet nanotubes are 5 times stiffer than steel. The maximum tensile strength of a carbon nanotube is 15 to 30 times that of steel, ranging between 30 and 60 gigapascals. So the interesting thing about carbon nanotubes is that they're really just sheets of graphene that have been rolled up in a certain way. Graphene sheets are single layers of carbon atoms with 3 sp2 hybrid orbitals. The interesting thing is that they actually have 3 sigma bonds in plane in an sp2 configuration, but the other pz orbital is perpendicular to the graphene plane, making a pi covalent bond. The graphite used in pencil lead is essentially layers of graphene that have been weakly bonded together with each other. That's why pencil lead is so soft. Nanotube properties really depend on how the sheets of graphene are rolled up. Different orientations result in different kinds of carbon nanotubes that exhibit unique and often very different properties. For instance, the electrical properties of armchair tubes act like a metal, and yet the chiral tubes act like semiconductors. Really, the only difference is the way that they've been twisted. So perhaps the most interesting aspect of carbon nanotubes are their thermal properties. Thermal conductivity in the axial direction of a carbon nanotube is 9 times greater than that of copper, and yet the thermal conductivity in the radial direction is about as conductive as soil. Electronics companies are now trying to utilize this unique ability of nanotubes to flow heat in specific directions for nanoscale heat removal. So in 2001, it cost $1,500 per gram of single-walled carbon nanotubes, also known as SWNTs. A gram is 4/10 the mass of a penny, the equivalent in its worth to the same fraction of a tax dollar designated to NASA as their total budget. Really small. By 2007, that price had dropped to $100 per gram of SWNT. Discovered by accident, researchers were trying to make C60 buckyballs with metal catalyst-infused electrodes, but air leaked into the electric arc chamber, resulting in C80 surrounding metal nitride molecules. Both the metal nitrides and the C80 buckyballs are normally very unstable, but when one is trapped inside the other, they become stable. Researchers are looking into using it as a contrast agent for MRI scans. Gadolinium is currently used, but it is toxic. To reduce risk, it is shielded in an organic compound, but this does not eliminate the risk, so the amount used must be limited. Buckyballs form stronger cages for the gadolinium, allowing more to be used and show 40 times better contrast than the current market offerings. In 2006, it was reported that scientists had successfully used buckyballs to help store information on the nanoscale. These scientists are looking to replace traditional bits in computers with quantum bits. Quantum physics allows for bits to exist in more than one state at once, making processing speeds 1 billion times faster. The problem with this is then isolating the bits from interacting with anything, since any interactions result in the bit dropping to a single state of matter. This isolation is the biggest challenge researchers face, and their recent successes came from the shielding of quantum bits by placing them inside of a buckyball. So real quickly, some further magic. What we could do with fullerenes is potentially create higher efficiency solar panels, develop smaller scale electronics, deliver radioactive metals to tumors without harming healthy cells, create hydrogen storage for fuel cells, and maybe even create a space elevator. And thankfully it isn't all magic. Some of the current applications are definitely used by Easton and Zyvex. Both of them utilize the high strength to weight ratio of carbon nanotubes to manufacture high performance bicycle parts and boat hulls respectively. Now I'd like to take a quick minute to thank everybody who was involved in this presentation, Derek, Courtney, Peter, and Dr. Farrell for an awesome 4 years. Long live metallurgy.
The Metal Hour. We don't just play heavy metal music. We also talk about metallurgy.